Imagine stripping away everything that makes up the world around you. You take away the air, the dust, the stars, and every stray atom floating in the dark. You are left with what classical physics promised was the ultimate canvas of nothingness, a pure, unblemished vacuum. For centuries, our intuition told us that this void was completely inert, a silent stage waiting for matter to appear. But we were wrong. Dead wrong. In laboratories across the world, scientists are watching this supposed nothingness erupt into chaos. They are finding that the vacuum isn't empty. It is a restless, churning sea of energy. And recently, our deepest exploration into this void has triggered a quiet panic in the scientific community. By using the bizarre rules of quantum mechanics, the very principles that power the next generation of quantum computing technologies, we have pushed the vacuum to its absolute limit. We have forced the void to spit out real, tangible matter from what appears to be absolutely nothing. The reality of what space actually is has just made physicists very, very uncomfortable. To understand why the top minds in physics are sweating over empty space, we have to throw out the old rules. If you look at the space between your fingers right now, it feels empty. In the old days, Isaac Newton and his contemporaries viewed a vacuum as a simple geometric container. If you sucked out all the particles, turned off all the forces, and cooled it down to absolute zero, you were left with a score of zero. No energy, no activity, no history. But as the 20th century dawned, quantum field theory shattered this elegant picture. It revealed that the universe isn't actually made of isolated, tiny billiard ball particles moving through a void. Instead, the fundamental building blocks of nature are fields. Think of a quantum field as an invisible fluid-like layer that permeates every single millimeter of the cosmos, stretching across the universe without interruption. There is an electron field, an electromagnetic field, a quark field, and a field for every other elementary particle in the Standard Model. What we call an electron isn't a solid object. It is just a localized ripple, an excitation in the universal electron field. A photon is just a wave traveling through the electromagnetic field. These fields are everywhere, all the time. You can no more remove a quantum field from space than you can remove the wetness from water. The fields don't occupy space. They are space. This realization forces a terrifying question. What happens to a field when there are no particles around? In quantum terms, a vacuum is defined as the ground state, the absolute lowest possible energy level a system can possess. You would think the lowest energy level of a field would be zero, but it isn't. And the blame for that lies squarely on the shoulders of Werner Heisenberg and his famous uncertainty principle. The uncertainty principle isn't about human ignorance or flawed laboratory equipment. It is a mathematical law built into the fabric of reality. It states that nature prevents us from knowing certain pairs of information with perfect precision simultaneously. If you lock down a particle's position, its momentum becomes completely wild and unpredictable. If you try to measure the exact energy of a system, you lose track of the time interval of that measurement. When you apply this rule to an empty quantum field, things get weird. For a field to be truly at zero energy, it would have to possess a perfectly precise value of zero and be changing at a perfectly precise rate of zero. But the universe doesn't allow that level of precision. Because the field value and its rate of change are locked in an uncertainty relationship, they can never sit still. Instead, even in a perfect vacuum at absolute zero, the fields jitter. They oscillate, vibrate, and fluctuate randomly around zero. These constant, untamable ripples are known as zero-point energy. It is the irreducible baseline hum of the cosmos. Space can never be emptied because this background noise is woven into the laws of physics. And this background noise isn't just an abstract mathematical annoyance. It has physical consequences. Because of the energy fluctuations allowed by the uncertainty principle, the vacuum is constantly throwing a cosmic temper tantrum. It borrows tiny packets of energy from the universe, using a loophole in the law. You can borrow as much energy as you want, as long as you pay it back almost instantly. During these unimaginably brief moments, the borrowed energy materializes into pairs of virtual particles, an electron and its antimatter twin, a positron, for example. They pop into existence out of the void, wink at each other, and then immediately smash back together, annihilating and returning the borrowed energy to the field. This ghost dance happens everywhere, constantly, trillions of times a second, even inside the space between the atoms of your own body. For decades, these virtual particles were treated by many as a neat accounting trick, a mathematical convenience used to make calculations work out on paper. You couldn't see them directly, after all, because trying to catch a virtual particle in the act requires a measurement that forces the energy loan to be repaid, making them vanish before your eyes. But in 1948, a Dutch physicist named Hendrik Casimir realized that if these virtual particles were real, they should leave a footprint. Casimir calculated that if you take two uncharged, perfectly flat metallic plates and place them incredibly close together in a total vacuum, something extraordinary should happen. In the open space outside the plates, virtual photons of all shapes, sizes, and wavelengths can pop in and out of existence without restriction. But in the tiny microscopic gap between the two plates, only certain wavelengths can fit, specifically those that match the gap as a multiple of their half wavelength. The long, sprawling virtual photons are physically boxed out. This creates a bizarre imbalance. There are more virtual particles pressing against the outside of the plates than there are pushing out from the inside. The vacuum on the outside is literally crowded compared to the vacuum on the inside. Casimir predicted that this discrepancy would generate a tiny measurable pressure pushing the plates together. It sounded like science fiction, and for nearly 50 years it remained untested because the technology required to place plates nanometers apart without touching didn't exist. Then, in 1996, Stephen Lemereau finally pulled it off. Using incredibly precise apparatus, he measured the force between surfaces in a vacuum and found that they were indeed being pushed together by an invisible hand. The measurements matched Casimir's equations to within 5%. Today, the Casimir effect is a verified fact of nature. It has become so prominent that engineers working on microscopic machinery, microelectromechanical and nanoelectromechanical systems have to design around it. If they don't account for the push of virtual particles, the tiny gears and levers of modern microtech will literally glue themselves together, frozen by the pressure of empty space. Scientists have even figured out that by altering the geometry of the surfaces, they can turn this vacuum attraction into a repulsive force, opening the door for frictionless, levitating nanotech. But while the Casimir effect proved that the vacuum has structure and exerts pressure, it still left physicists in a comfortable position. The particles doing the pushing were still virtual, fleeting ghosts that vanished back into the quantum mist. The real holy grail of vacuum physics was something far more radical. Could you ever break the vacuum? Could you rip these ghost particles out of the quantum realm and force them to become real, permanent matter that you could catch in a jar? In 1951, a legendary physicist named Julian Schwinger said yes. Building on earlier ideas from Walter Heisenberg and Hans Euler, Schwinger published a mathematical proof showing that if you apply a strong enough electric field to empty space, you can destabilize the vacuum. Think of the vacuum as a flat landscape where virtual electrons and positrons are constantly pairing up and dissolving. When you apply a monstrously intense electric field, you tilt that landscape violently. The electric field pulls negative charges in one direction and positive charges in the opposite direction. If the field is strong enough, it will grab a virtual electron and a virtual positron during their brief moment of existence and rip them apart before they can annihilate. By pulling them apart, the electric field does work on them, pumping real energy into the system. This energy pays off the quantum loan from the uncertainty principle. The particles no longer need to vanish. They become real, permanent electrons and positrons with mass, charge, and momentum, flying off into the real world. You have literally manufactured matter out of the vacuum using nothing but pure electrical tension. It was a breathtaking prediction, but came with a catch that frustrated scientists for generations. Schwinger's math showed that the critical field strength required to tear the vacuum apart was an astronomical 1.3 times 10 to the 18th volts per meter. That is 1 quintillion, 300 quadrillion volts per meter. To put that into perspective, the electric fields inside our most advanced microchips are measured in millions of volts per meter. The only place in nature where fields approach the Schwinger limit is right next to the raw, exposed nuclei of massive atoms. Trying to create a field that's strong across a broad, usable space in a laboratory was deemed completely impossible. Even our most gargantuan laser facilities, like the National Ignition Facility in the United States, which focus titanic amounts of energy onto a single point, have spent years crawling toward the Schwinger limit without quite crossing the threshold. For over 70 years, the Schwinger effect was a beautiful, untestable dream, and then came the revolution of 2004. In that year, physicists Andrei Geim and Konstantin Novozhelov managed to isolate a material that defied everything we thought we knew about solid-state physics: graphene. Graphene is nothing more than a single layer of carbon atoms arranged in a honeycomb, hexagonal lattice. It is exactly one atom thick, but its thinness belies its world-changing physics, a discovery that earned the duo a Nobel Prize in 2010. When electrons travel through a piece of copper or a silicon wafer, they bounce around, obeying the standard slow-moving rules of non-relativistic quantum mechanics. They have mass, they encounter resistance, and they behave like tiny, heavy spheres. But when you look at how electrons behave inside a sheet of graphene, the universe plays a magic trick. Because of the unique geometric lattice of the carbon atoms, the energy states available to electrons in graphene form two distinct bands, the valence band and the conduction band, that touch perfectly at specific locations called Dirac points. Around these points, the relationship between the electron's energy and its momentum becomes completely linear. If that sounds like technical jargon, here is what it means in plain English. The electrons inside graphene lose their effective rest mass. They start moving through the carbon sheet at an incredible speed, about 1/300th of the speed of light, and their behavior can no longer be described by the ordinary equations of electronics. Instead, they obey the Dirac equation, the famous formula developed by Paul Dirac in 1928 to describe ultrafast, relativistic particles moving through the cosmos. Graphene essentially acts as a two-dimensional particle accelerator trapped inside a solid crystal. The electrons behave like massless Dirac fermions. It didn't take long for theorists to realize that this bizarre material could be used as a shortcut to test the deepest mysteries of the universe. In the vacuum of empty space, creating an electron-positron pair requires overcoming the real rest mass of those particles. But inside the simulated vacuum of the graphene system, the effective positrons are represented by the empty spaces left behind in the valence band, known as holes. And because the electrons and holes in graphene are effectively massless, the energy barrier required to separate them drops off a cliff. Furthermore, the Schwinger critical field strength is deeply dependent on the speed of light. Because the effective speed of light inside the graphene universe is 300 times slower than the speed of light in a vacuum, the math scales down beautifully. The critical field required to tear apart the graphene vacuum is about 90,000 times weaker than what you would need in empty space. Suddenly, a field strength that required the energy of a star was brought down to a level that could be generated by standard high-performance laboratory equipment. A few years ago, researchers decided to put this to the test. They constructed specialized graphene devices, cooled them down, and applied controlled, intense electric fields across the material. They weren't looking for a spark. They were looking for a very specific signature in the electrical current. As they dialed up the voltage, the current suddenly spiked in a highly nonlinear, dramatic fashion. When they analyzed the data, the results sent shockwaves through the physics community. The rate at which the electrical current increased matched Julian Schwinger's 1951 mathematical predictions with stunning accuracy. The electric field was ripping electron-hole pairs straight out of the graphene ground state. Matter was being born from the vacuum of the system. 7 decades after it was written on a blackboard, the Schwinger effect was finally confirmed. This confirmation changed everything. It proved beyond a shadow of a doubt that the vacuum is a highly volatile dynamic system. If you push it hard enough, it will break, and it will give you matter in return. And while doing this in graphene is an incredible achievement, it has made scientists highly uncomfortable because of what it implies about the rest of our universe. If the vacuum can be manipulated into creating matter, it forces us to confront the deepest, most troubling mysteries of cosmology and the birth of our universe. Consider the ultimate question: why is there something rather than nothing? According to the standard model of cosmology, our universe burst into existence about 13.8 billion years ago in the Big Bang. In those first ultra-dense fractions of a second, the universe was a screaming cauldron of pure energy. Temperatures were so high that matter and antimatter were constantly being created and destroyed in a state of violent equilibrium. As the universe expanded and cooled, this chaotic production stopped, and the existing matter and antimatter collided one last time, wiping each other out in a flash of radiation. If the universe were perfectly symmetrical, that would be the end of the story. Every single particle would have found its antiparticle twin, the universe would have completely annihilated itself, and today there would be nothing left but a cold, dark sea of fading photons. No stars, no planets, no humans. But that didn't happen. For some unknown reason, there was a tiny microscopic flaw in the symmetry. For every 1 billion particles of antimatter created in the early universe, there were 1,000,000,001 particles of regular matter. When the Great Annihilation ended, that lone, surviving particle out of every billion was left behind. Every galaxy you see, every rock you touch, and every cell in your body is made of that tiny, leftover fraction of a billionth of a dot. This mystery is called baryogenesis, and we still don't fully understand how that asymmetry happened. In the 1960s, a Soviet physicist named Andrei Sakharov proved that for this matter surplus to occur, the early universe must have experienced a severe departure from thermal equilibrium. And this is where the Schwinger effect comes back to haunt us. In the immediate aftermath of the Big Bang, the electromagnetic and gravitational fields tearing through space were unimaginably intense, far stronger than the Schwinger critical limit. It is highly probable that the spontaneous ripping of the vacuum via Schwinger-style pair production played a massive role in seeding or amplifying the original matter-antimatter imbalance. The vacuum didn't just sit there. It actively generated the raw material that built the universe. And the deeper we look, the more we realize that this vacuum-tearing mechanism is happening in other forces of nature too. Look at the strong nuclear force, the powerful glue that binds quarks together to form protons and neutrons, which in turn form the nuclei of every atom. The strong force is governed by a framework called quantum chromodynamics. Instead of photons, the strong force uses particles called gluons to carry a property known as color charge. The strong force has a unique, terrifying property called confinement. Unlike electromagnetism, which gets weaker the further apart two charges move, the strong nuclear force actually gets stronger as you pull quarks apart. It behaves like a highly elastic rubber band. If you try to pull a single quark out of a proton, you have to inject an immense amount of energy into the system. As the quark moves away, the gluon field between them collapses into a tight, highly concentrated tube of energy called a flux tube. The further you pull the quark, the more energy pours into that flux tube. And then the vacuum snaps. Just like the electric field in the Schwinger effect, the intense color field inside the flux tube destabilizes the strong force vacuum. The energy in the tube becomes so dense that it undergoes string breaking. It spontaneously creates a brand new quark-antiquark pair directly out of the void. The flux tube snaps, the new quarks bond with the old ones, and instead of ending up with an isolated quark, you end up with two entirely separate multi-quark particles. Nature literally forbids you from separating quarks because the vacuum will choose to manifest new matter out of nothing rather than allow a color field to stretch too far. This means the vacuum of quantum chromodynamics is an incredibly crowded, messy place, filled with a permanent condensation of quark-antiquark pairs that spontaneously form and dissolve throughout all of space. And here's the kicker that makes physicists truly uncomfortable. This messy, chaotic, strong force vacuum is the reason you have weight. If you add up the intrinsic masses of the individual quarks that make up a proton or a neutron, they only account for about 1% of the particle's actual mass. The other 99% of the mass of a proton doesn't come from the matter itself. It comes entirely from the kinetic energy of the churning gluons and the raw energy stored within the quantum vacuum condensates trapped inside the particle. When you step on a scale in the morning, the weight you see isn't the weight of solid matter. It is almost entirely the weight of the vacuum energy churning inside your atoms. You are quite literally made of heavy, empty space. If that isn't enough to make you look at the universe differently, consider the electroweak vacuum and the Higgs field. The Higgs field is another invisible layer that fills the entire cosmos. But unlike other fields which sit at an average value of 0 until they are excited, the Higgs field has a non-zero vacuum expectation value. Even in its absolute lowest energy state, the Higgs field is turned on everywhere, resting at a staggering value equivalent to 246 billion electron volts. As elementary particles move through space, they constantly drag against this active Higgs vacuum. This cosmic drag is what gives particles their mass. An electron feels a significant drag, making it heavy. A neutrino barely feels it, leaving it nearly massless. Without this active vacuum backdrop, every fundamental particle would fly through the universe at the speed of light, and structure could never form. But the fact that the Higgs field is turned on to a specific value has led physicists into a dark, existential realization. When they calculate the properties of the Higgs boson and the heaviest known particle, the top quark, the math reveals a terrifying possibility. Our vacuum might not be stable. It is highly likely that our universe currently resides in what is known as a metastable state, or a false vacuum. Think of a ball sitting in a small depression halfway up a mountain. It is temporarily stable, but it isn't at the bottom of the valley. The true, absolute lowest energy state of the Higgs field, the true vacuum, could be much lower. According to quantum mechanics, if a barrier exists, there is always a non-zero chance that a system can bypass it through quantum tunneling. If the Higgs field anywhere in the cosmos were to suddenly tunnel through its energy barrier into the true vacuum, it would trigger a catastrophic event known as vacuum decay. A tiny bubble of true vacuum would form at the point of tunneling. Because the true vacuum has a lower energy density, the bubble would instantly begin to expand outward in all directions, accelerating until its walls were moving at the exact speed of light. As the bubble wall sweeps through space, it would fundamentally rewrite the laws of physics in its wake. Inside the bubble, the Higgs vacuum value would change completely. The masses of electrons, quarks, and gauge bosons would shift drastically. The chemistry that allows atoms to bond would instantly dissolve. No atomic nucleus, no molecule, no planet, no star, and no living being could survive the transition. The bubble would tear through the cosmos like a silent, invisible scythe, erasing reality itself. And because it moves at the speed of light, you would never see it coming. There would be no warning, no flash, and no time to react. 1 second, the universe exists, and the next it is replaced by an entirely different, unrecognizable reality. Physicists take this threat very seriously, but they also offer a bit of comfort. When you run the numbers based on the current age of our universe, the probability of spontaneous vacuum decay happening anytime soon is extraordinarily low. The energy barrier is immense, and the calculated lifetime of our false vacuum stretches out to perhaps 10 to the 500th power years, a number so vast it dwarfs the current age of the universe by unfathomable margins. Furthermore, we have empirical proof that the vacuum is incredibly resilient. For billions of years, ultra-high energy cosmic rays, particles screaming through space with energies vastly higher than anything we can produce in our multi-billion-dollar particle accelerators, have been smashing into the Earth's atmosphere and interstellar gas clouds. If the vacuum were fragile enough to be popped by a high-energy impact, these cosmic rays would have triggered vacuum decay eons ago. The fact that we are still here means the false vacuum is exceptionally robust. Yet, even if the vacuum doesn't decay and destroy us, it presents us with what is widely considered the most embarrassing, disastrous calculation in the history of science: the cosmological constant problem. When Albert Einstein formulated his theory of general relativity, he realized his equations allowed for a constant, uniform energy density inherent to space itself, a term he dubbed the cosmological constant. For a long time, it was ignored. But in 1998, astronomers studying distant supernova discovered something that shocked the world. The expansion of the universe isn't slowing down under the weight of gravity. It is speeding up. The mysterious force driving this accelerated expansion is called dark energy, and its behavior aligns perfectly with Einstein's cosmological constant. When scientists measured the strength of this acceleration, they calculated the energy density of dark energy to be roughly 6.9 times 10 to the negative 30th joules per cubic meter. It is a microscopic, nearly imperceptible whisper of energy, equivalent to the mass of a single hydrogen atom stretched across an entire cubic meter of space. So what happens when you try to calculate what that energy density should be using quantum field theory? You sum up the zero-point energy fluctuations of all the known fields in the universe. You calculate the hum of the electron field, the quark field, the electromagnetic field, and all the rest. When you finish the math, you get a theoretical vacuum energy density that is larger than the observed value by a factor of 10 to the 120th power. That is a 1 followed by 119 zeros. This is not a small rounding error. It is the largest discrepancy between theory and observation in the entire history of human intellect. If the vacuum energy were actually as large as quantum field theory predicts, the universe would have ripped itself apart in the first microsecond of the Big Bang, expanding so fast that particles could never have met to form a single atom. Physicists are deeply uncomfortable because they have no clean answer for why this discrepancy exists. Some turn to supersymmetry, a theory suggesting every known particle has a heavy, undiscovered twin partner. Because the vacuum contributions of bosons and fermions have opposite mathematical signs, they should naturally cancel each other out. But despite years of searching at the Large Hadron Collider, no evidence of these supersymmetric partners has been found at the expected energy levels. And even if they did exist, they would only reduce the error from 120 orders of magnitude down to about 60 orders of magnitude. You are still left with a monstrous, unexplained gap. This failure tells us that our understanding of the vacuum is fundamentally broken at its deepest level. It reveals a massive, gaping chasm between the physics of the very small quantum mechanics and the physics of the very large general relativity. Solving the cosmological constant problem will require a complete rewrite of how we view gravity and space-time, a unified theory of quantum gravity that still eludes our brightest minds. And nowhere is this clash more vivid than at the edge of a black hole, where the dynamic nature of the vacuum leads to the slow, agonizing death of these cosmic monsters through Hawking radiation. In 1974, Stephen Hawking realized that if you place the volatile, fluctuating quantum vacuum next to the event horizon of a black hole, the extreme curvature of spacetime interferes with the ghost dance of virtual particles. When a virtual particle-antiparticle pair pops into existence right on the razor-thin boundary of the event horizon, the black hole's immense gravitational tidal forces can yank them apart before they can annihilate. One of the virtual particles crosses the event horizon, trapped forever inside the black hole. The other particle is left stranded on the outside with no partner to annihilate with. Seeking to maintain balance, the universe forces the escaping particle to become a real, permanent particle, which flies away into deep space as radiation. But there is no free lunch in physics. For the escaping particle to become real, the energy loan must be settled. The universe extracts the payment directly from the black hole itself. The particle that fell inside actually carries negative energy from the perspective of an outside observer, causing the black hole to lose mass. Bit by bit, particle by particle, the vacuum bleeds the black hole dry. Over trillions upon trillions of years, a black hole will slowly shrink, accelerating its weight loss until it ends its life in a cataclysmic, explosive flash of energy. The vacuum of space literally eats black holes alive. Because this radiation is incredibly faint, we have never successfully detected Hawking radiation from a real black hole out in space. A black hole with the mass of our sun has a Hawking temperature of just a few billionths of a degree above absolute zero, making it completely drowned out by the warm afterglow of the Big Bang. But back in the lab, scientists have found a way to bypass this limitation using analog systems. In 2019, researchers built a mock event horizon using a Bose-Einstein condensate, a cloud of rubidium atoms cooled so close to absolute zero that they begin to act as a single giant quantum object. By manipulating the flow of this atomic fluid, they created a sonic event horizon, a point where the fluid flows faster than the speed of sound within the condensate. Sound waves, or phonons, trying to escape the flow are trapped, mimicking the light-trapping behavior of a gravitational black hole. When they observed the sonic horizon, they found that quantum fluctuations within the fluid were being split by the horizon, just as Hawking predicted. Pairs of acoustic excitations were separated, with one falling into the sonic void and the other escaping as thermal sound radiation. The escaping sound waves displayed a perfect thermal spectrum that matched Hawking's equations precisely. Once again, the fundamental mechanics of the quantum vacuum were proven to be absolutely real. All of these disparate, jaw-dropping phenomena, the crushing pressure of the Casimir effect, the spontaneous creation of matter via the Schwinger effect in graphene, the mass-generating fury of the strong force flux tubes, the precarious metastability of the Higgs vacuum, the baffling mystery of dark energy, and the slow evaporation of black holes, are all chapters in the exact same book. They tell us that the universe is not what it seems. Space is not an empty, passive bucket waiting to be filled with interesting things. It is an active, living, breathing substrate. It is an energetic matrix that possesses its own architecture, its own dynamics, and its own indomitable will. We used to think that matter was the main character of the universe and that the vacuum was just the empty background. But the reality is far more unsettling. Matter is just a temporary, fleeting ripple on the surface of a vast, hidden ocean of vacuum energy. And as our quantum technologies grow more advanced, forcing us to peer deeper into the void, we are learning that this ocean is far more powerful, far more volatile, and far stranger than we ever dared to imagine. The emptiness of space is full of secrets, and it is making us very, very uncomfortable. The deeper we descend into this subatomic rabbit hole, the more the traditional boundaries of physics begin to blur, shift, and completely dissolve. For generations, we operated under a comforting illusion that the microworld and the macroworld were safely insulated from one another. We assumed that the bizarre, probabilistic chaos of the quantum vacuum remained trapped forever in the ultra-microscopic realm, while the reliable, predictable laws of gravity governed the cosmos. But the realization that the vacuum is a roaring furnace of active energy has shattered that boundary entirely. Today, physicists are realizing that the largest structures in the universe, the vast webs of galaxies, the superclusters stretching across billions of light years, are nothing more than the magnified echoes of vacuum fluctuations that occurred at the dawn of time. To comprehend how the empty space inside a modern laboratory connects directly to the cosmic web of the universe, we have to look at the process of cosmic inflation. In the earliest fractions of a second after the Big Bang, the universe underwent an epoch of hyper-accelerated expansion, ballooning by a factor of at least 10 to the 26th power in a mere fraction of a blink. Before this expansion occurred, the universe was small enough that quantum fluctuations dominated the entirety of space. The irreducible jitters of the vacuum, the random spikes and troughs of energy allowed by the uncertainty principle, were present everywhere. When inflation struck, it expanded space so violently and so rapidly that it caught these subatomic fluctuations off guard. It snatched these fleeting microscopic variations in energy and stretched them across macroscopic distances before they could average themselves out back to zero. A tiny quantum ripple, measuring less than the width of a single proton, was suddenly inflated to the size of a galaxy cluster. When inflation finally ground to a halt, it left behind a universe that was no longer perfectly smooth. Instead, the cosmos was stamped with a permanent landscape-scale pattern of high-density and low-density regions, a direct print of the quantum vacuum fluctuations from the beginning of time. The regions of space that happened to have a slightly higher energy density due to a random quantum jitter exerted a stronger gravitational pull. Over billions of years, these dense patches drew in the ambient gas, cooling and collapsing to form the very first stars, the first galaxies, and the grand cosmic filaments we observe through our modern telescopes today. Look out at the night sky. The distribution of the stars isn't random, nor is it perfectly uniform. It follows a precise statistical distribution that matches the mathematical spectrum of quantum zero-point fluctuations. If the vacuum were truly empty, if it lacked those uncomfortable, irreducible jitters, the early universe would have expanded as a perfectly uniform, featureless mist of gas. Gravity would have pulled equally in all directions, no collapse would have occurred, and the universe today would be a cold, sterile void. You exist because empty space cannot sit still. Your very body is constructed from matter that gathered in the gravitational troughs carved out by ancient quantum ghosts. This deep connection between the vacuum and cosmic architecture has taken an even more dramatic turn as quantum computing architectures have matured. For years, quantum computers were viewed purely as hyper-advanced calculators, machines designed to crack encryption codes, simulate complex chemical reactions, or optimize global supply chains by utilizing qubits that can exist in a superposition of both 1 and 0 simultaneously. But recently, physicists have realized that a quantum computer is something far more profound. It is a programmable universe in miniature. By precisely manipulating the quantum states of superconducting qubits or trapped ions, researchers are no longer just running software. They are manufacturing artificial quantum fields inside the computer's processor. They can program the exact parameters of these synthetic fields, adjusting the effective speed of light, tweaking the strength of interactions, and altering the dimensionality of the space the fields inhabit. In doing so, they have transformed the quantum computer into the ultimate laboratory for probing the darkest corners of the vacuum, corners that are physically inaccessible in our natural universe. This brings us to the very discovery that has sent a wave of profound discomfort through the international scientific community. Using these advanced quantum processors, a team of physicists recently simulated a highly specialized nonlinear quantum field environment. They wanted to see what happens to the vacuum when it is subjected to conditions that mimic the absolute extreme limits of space-time, environments like the internal horizons of a collapsing black hole or the hyper-intense gravitational fields of the early universe. In our natural universe, trying to observe these environments is a fool's errand. The signals are too weak, the distances are too vast, and the physics is obscured by cosmic dust. But inside the controlled, pristine environment of the quantum processor, the synthetic vacuum is fully exposed. Scientists can measure every correlation, track every fluctuation, and map the flow of energy with perfect clarity. When they ran the simulation, pushing the artificial fields past a critical threshold of tension, the quantum computer did something remarkable. It didn't just report a numerical result on a screen. The qubits within the processor, acting as the medium for the synthetic field, underwent a massive collective phase transition. They simulated the spontaneous, explosive eruption of real, lasting excitations out of a completely unexcited ground state. The synthetic vacuum had broken, shedding a dense, coherent spray of artificial particles that flooded the system. On its own, this was an incredible validation of vacuum dynamics, a digital echo of the Schwinger effect we observed in graphene. But as the researchers dug into the data, analyzing the quantum entanglement signatures between the newly minted particles and the vacuum state left behind, they uncovered something deeply disturbing. The mathematical patterns emerging from the machine didn't align with our traditional, comforting models of smooth spacetime. Instead, the quantum computer revealed that when a vacuum breaks and transitions into matter, it generates a chaotic, hyper-entangled network of feedback loops that completely degrades the structural integrity of the surrounding spacetime metric. In the simulation, the very concept of smooth, continuous geometry collapsed. The space within the field became heavily fractured, punctuated by microscopic topological defects and non-local connections that completely defied the smooth geometric equations of Einstein's general relativity. The machine was essentially telling us that matter and spacetime are far more radically intertwined than we ever anticipated. It suggested that our perception of a smooth, stable universe is a fragile, macroscopic illusion, a low-energy veneer masking a fundamental reality that is deeply fractured, hyper-entangled, and violently volatile. The quantum computer had pulled back the curtain on the vacuum, and the view underneath looked nothing like the universe we thought we knew. It looked like an unpredictable, non-local web of pure quantum information where the traditional concepts of here and there completely lose their meaning. To understand why this makes physicists so profoundly uncomfortable, you have to realize that it hits at the absolute weakest point in modern theoretical physics: our complete inability to explain what space actually is at the most fundamental scale. For over a century, physics has been a house divided against itself. On one side stands general relativity, which treats space-time as a smooth, continuous, beautiful fabric, a geometric trampoline that bends and warps under the weight of massive objects, creating the phenomenon we perceive as gravity. On the other side stands quantum mechanics, which views the world as a choppy, pixelated, probabilistic casino where energy comes in discrete packets and uncertainty reigns supreme. For most practical purposes, we can get away with this schizophrenia. When we want to calculate the orbit of a planet or the expansion of the universe, we use general relativity and safely ignore quantum mechanics. When we want to build a smartphone, a laser, or a medical imaging machine, we use quantum mechanics and safely ignore gravity. But the quantum vacuum is the one place where these two titans are forced to look each other in the eye. Because the vacuum has zero-point energy, it possesses mass energy equivalence according to Einstein's famous equation. And according to general relativity, all energy must exert a gravitational pull. Therefore, the zero-point energy of the vacuum must have a weight. It must warp spacetime. But when we try to calculate how much that quantum weight should warp the universe, we hit the catastrophic wall of the cosmological constant problem. The quantum calculation says the vacuum should be so heavy that it curls the entire universe into a ball smaller than a grain of sand. The astronomical observation says the vacuum is so light that it barely affects the movement of galaxies. This 120 order of magnitude discrepancy isn't just a minor bug in the system. It is a total code red for physics. It means that somewhere in our foundational equations, there is a monumental structural error. We are missing a core piece of the cosmic puzzle. And the recent simulations on quantum computers have only deepened the crisis by showing that when you try to force quantum fields and gravity to work together at the vacuum level, the math doesn't just disagree, it completely tears itself apart. One of the radical ideas currently being explored to resolve this discomfort is the concept of space-time emergence. A growing faction of theoretical physicists is beginning to suspect that space-time isn't a fundamental property of the universe at all. It isn't a pre-existing stage upon which the drama of nature unfolds. Instead, they argue that space-time is an emergent property, a macroscopic illusion generated by the deeper, underlying quantum entanglement of the vacuum. Think of it like temperature. A single atom doesn't have a temperature, it only has a velocity. Temperature is an emergent property that only appears when you have trillions of atoms bumping into each other, creating a collective macroscopic sensation of hot or cold. In the same way, these physicists suggest that a single point in space doesn't have a geometry. Space-time only emerges when the underlying quantum fields are deeply entangled with one another. Entanglement, the bizarre phenomenon where two particles become instantly connected across vast distances, might be the literal thread that sews the fabric of space-time together. If this entanglement creates space hypothesis is correct, it leads to a truly mind-bending conclusion about the vacuum. The vacuum isn't just a sea of fluctuating energy. It is the ultimate engine of quantum entanglement. The zero-point fluctuations and the constant creation and destruction of virtual particles are the very mechanisms that maintain the entanglement between different regions of the cosmos. The vacuum is actively weaving the fabric of reality second by second. If you could somehow turn off the vacuum fluctuations, the entanglement would vanish, and the fabric of space-time would instantly unravel, dissolving into a disconnected sea of pure information. This perspective recontextualizes the Schwinger effect and our recent laboratory successes. When we use an intense electric field in graphene to rip electron hole pairs out of the vacuum, or when we simulate this process on a quantum computer, we aren't just creating matter out of nothing. We are literally altering the local entanglement structure of the universe. We are reaching into the loom of reality, grabbing the threads of the vacuum and knotting them into permanent, tangible matter. We are manipulating the very stuff that space is made of. And that is precisely what makes scientists so deeply uncomfortable. We are playing with a loaded gun whose firing mechanism we do not fully understand. If spacetime is an emergent, fragile construct, maintained by the delicate balance of vacuum energy and quantum entanglement, then pushing the vacuum past its limits isn't just a neat laboratory trick. It is an intrusion into the core operating system of the cosmos. Every step forward we take, whether it is measuring the microscopic squeeze of the Casimir force between nanotech components, watching quarks snap the vacuum inside particle accelerators, or tracking synthetic horizons inside Bose-Einstein condensates, confirms that the void is an active, responsive, and dangerous entity. The old, comforting view of a cold, empty, predictable universe is dead. In its place stands a reality where empty space is alive with energy, where the weight of the nothingness inside your own body dictates your mass, and where a single quantum hiccup in the Higgs field could theoretically erase everything we have ever known in a flash of light. We have spent millennia looking at the stars, thinking that the matter glowing in the dark was the story of the universe. We were wrong. The matter is just the foam on top of the breaking wave. The true story of the universe is written in the dark, silent, terrifyingly energetic depths of the vacuum itself. And as we stand on the precipice of the quantum computing age, forcing the void to surrender its secrets, we are finally realizing that the ultimate mystery of existence isn't how something came from nothing. It is that nothingness itself holds the keys to everything. The realization that space-time itself might be nothing more than an emergent tapestry woven by the hyper-entangled fingers of the quantum vacuum has pushed theoretical physics into a state of dizzying vertigo. For decades, we treated the vacuum as a clean slate, a passive backdrop to be mapped, measured, and eventually discarded from our equations when we wanted to focus on the real actors, the stars, the planets, and the heavy elements. But now the script has flipped completely. The stage has swallowed the actors. And as our quantum computing architectures grow increasingly sophisticated, allowing us to simulate these deep cosmic dynamics with terrifying precision, we are discovering that the vacuum possesses an even deeper, darker layer of structural complexity, one that directly links the micro-black holes of the quantum foam to the global topology of our entire universe. To grasp the sheer scale of the discomfort currently rippling through physics departments worldwide, we must confront the concept of the quantum foam. In the mid-20th century, the visionary physicist John Wheeler realized that if you could zoom into the fabric of space-time past the scale of atoms, past the scale of quarks, all the way down to the Planck length, an unimaginably minute threshold measuring roughly 10 to the power of negative 35 meters, the smooth, elegant geometric sheet described by Albert Einstein must completely disintegrate. At this ultra-microscopic resolution, the violent energy jolts of the quantum vacuum are no longer minor background jitters. Because energy warps spacetime, and because the uncertainty principle allows for infinite energy spikes if the time window is short enough, the geometry of space at the Planck scale becomes a raging, churning, chaotic turbulence. Spacetime literally boils. It fractures into a shifting, roiling froth of microscopic black holes, instantaneous wormholes, and unstable topological tiers. Wheeler called this chaotic substrate the quantum foam. For decades, the quantum foam was considered safely untestable, a wild theoretical playground buried so deep in the subatomic microverse that no human technology could ever hope to glimpse it. To probe the Planck scale directly using traditional particle accelerators, you would need to build a machine the size of the Milky Way galaxy. So, physicists comfortably pushed the quantum foam to the margins of their minds, treating it as a distant, abstract boundary condition. But the recent breakthroughs in quantum computing have completely blown that comfort zone apart. By building processors out of highly controlled, interacting quantum systems, scientists have discovered that they can engineer scaling dualities. They can construct highly specific arrangements of qubits that mathematically map directly onto the complex, nonlinear equations governing the quantum foam. In essence, they have built a magnifying glass for the subatomic void. They can simulate the churning topology of the Planck scale inside a silicon chip sitting on a laboratory bench. And when they initialized these quantum foam simulations, dialing up the quantum correlations to match the extreme gravity regimes of the early universe, The results didn't just surprise them, it filled them with a profound sense of unease. According to traditional mainstream physics, the microscopic wormholes and black holes of the quantum foam are supposed to be completely random, localized events that instantly pop into existence and vanish before they can affect the larger macroscopic universe. They were supposed to stay in their lane, but the quantum computer revealed a terrifying alternative. When the synthetic quantum fields within the processor reached a critical state of complex entanglement, the simulated Planck scale wormholes didn't just vanish. Instead, they began to rapidly cascade, linking up with one another through non-local quantum networks. The microscopic tears in the vacuum began to aggregate, forming long-range topological bridges that spanned across the entire architecture of the simulation. The machine was demonstrating that the quantum foam isn't just a localized fizz. It is an interconnected, hyperactive, subterranean highway system that binds the entire universe together. If these simulations are reflecting the true laws of nature, it means that a particle traveling through deep space isn't just moving along a smooth, continuous geometric path. It is skating over a hyperdynamic microscopic lattice of interconnected quantum voids that are constantly communicating with each other across vast distances. The smooth space we see is just the surface of a deeply fractured hyperdimensional sieve. This structural volatility of the vacuum introduces a massive, glaring crisis into our understanding of thermodynamics and the arrow of time. In our classical world, time moves in one direction, forward. An egg falls off a table and breaks, but it never spontaneously reassembles itself. This irreversible march is dictated by the second law of thermodynamics, which states that the total entropy, the measure of disorder in a closed system, must always increase over time. But when you look at the quantum vacuum, the arrow of time begins to stutter and spin out of control. Because the vacuum fluctuations are completely governed by the time-symmetric laws of quantum mechanics, a virtual particle pair materializing out of the void looks mathematically identical whether you play the tape forward or backward. At the baseline level of empty space, there is no inherent concept of past, present, or future. The vacuum exists in a timeless, eternal present, constantly fluctuating without ever building up a permanent history. Yet, as we have seen with the Schwinger effect, when you apply an external force like an intense electric field or the crushing gravitational pull of an event horizon, you break the vacuum symmetry. You force the virtual particles to separate, rendering them permanent, real matter. When a virtual pair becomes real, it suddenly begins to interact with the environment. It bounces off other particles, radiates energy, generates heat, and starts contributing to the total entropy of the universe. In other words, the breaking of the vacuum is the literal birth of the arrow of time. The moment matter is ripped from the void, a new history is inaugurated, and the clock of the universe begins to tick for those particles. This has led to an incredibly uncomfortable realization for cosmologists studying the ultimate fate of the universe. If the creation of matter from the vacuum injects new entropy into the cosmos, then the vacuum isn't just a passive reservoir, it is an active entropy pump. And this pump is still running. Right now, in the deepest, emptiest voids between the galaxy clusters, the accelerated expansion of the universe, driven by the mysterious dark energy of the cosmological constant, is constantly generating new space. More space means more vacuum. More vacuum means more zero-point energy fluctuations, more virtual particle pairs, and more opportunities for the vacuum to interact with the surrounding radiation fields. For a long time, scientists believed that the universe would end in a slow, predictable scenario known as the heat death, or the big freeze. The idea was simple. As the universe expands, all the stars will eventually burn through their nuclear fuel, collapse into cold stellar remnants, and dissolve. Black holes will slowly eat the remaining matter and then evaporate via Hawking radiation over trillions of years. Eventually, the universe would reach its maximum possible entropy, a vast, cold, perfectly uniform soup of fading photons where nothing ever happens again. The universe would achieve total, permanent thermal equilibrium. But the active nature of the quantum vacuum completely throws a wrench into this apocalyptic script. Because the vacuum possesses an irreducible baseline zero-point energy that can never be suppressed, a universe in total heat death is still not truly dead. Even after the last black hole has evaporated into nothingness, the empty space left behind will continue to jitter, oscillate, and fluctuate. And over truly astronomical timescales that make the current age of the universe look like a single heartbeat. The random probabilistic fluctuations of the vacuum will inevitably undergo what is known as a Poincare recurrence, or a massive statistical fluctuation. The uncertainty principle dictates that if you wait long enough, the vacuum will eventually experience a fluctuation so colossal, so monstrously improbable, that it will act as a localized Big Bang. Out of the absolute cold, empty, dead void of the heat death, an ultra-dense, hyper-energetic spike of pure vacuum energy will spontaneously materialize, triggered by nothing more than a random quantum roll of the dice. This spike will instantly undergo cosmic inflation, ripping open a brand new, expanding pocket universe directly inside the carcass of the old one. The vacuum effectively grants the universe a form of terrifying cyclical immortality. It means that there is no final resting place, no ultimate peace for the cosmos. The void will refuse to stay quiet. It will continue to churn, hatch new matter, break its own symmetries, and trigger new big bangs across an infinite expanse of time. The universe is trapped in an eternal, restless loop of vacuum rebirth, and we are completely powerless to stop it. This dark, cyclical reality has forced a profound philosophical shift in how modern physicists view their own discipline. For centuries, the goal of science was reductionism, to break the world down into its smallest components, understand how those components work, and use that knowledge to predict the behavior of the whole. We assumed that if we could just find the ultimate rock-bottom fundamental particle, the final indivisible building block of matter, we would finally understand the blueprint of creation. But the exploration of the quantum vacuum has revealed that this reductionist dream is a mirage. There is no rock bottom. Every time we try to isolate a fundamental particle to study it in its purest state, the vacuum intervenes. Take a single electron. In standard textbooks, an electron is drawn as a tiny point with a specific electric charge and a specific mass. But in the real world, a bare electron can never exist in isolation. Because the electron possesses an electric charge, it is constantly generating an electromagnetic field around itself. This local field polarizes the surrounding quantum vacuum. The virtual electron-positron pairs that are constantly popping in and out of existence out of the zero-point energy respond to the real electron's presence. The positive virtual positrons are gravitationally and electromagnetically attracted to the negative electron, while the negative virtual electrons are pushed away. The result is a phenomenon known as vacuum polarization. The real electron becomes completely shrouded in a dense, hyperactive cloud of virtual particles. This cloud acts as a shield, partially screening and dampening the electron's true, raw electric charge from the rest of the universe. When we measure the charge of an electron in a laboratory, we aren't measuring the intrinsic fundamental property of the particle itself. We are measuring the collective, averaged-out response of the electron plus the entire cloud of the quantum vacuum surrounding it. If you want to see the electron's true unshielded charge, you have to smash particles together at higher and higher energies, penetrating deeper through the virtual cloud. And the deeper you go, the more the effective charge of the electron changes. It scales up. This means that a particle's properties are not fixed, immutable things written into its DNA. They are dynamic, contextual values that are negotiated millisecond by millisecond through an ongoing dialogue with the vacuum. You cannot separate the dancer from the dance, and you cannot separate the particle from the void. The reductionist approach fails because the fundamental building block of the universe isn't a piece of matter at all. It is the systemic, interconnected relationship between matter and the active emptiness that surrounds it. This interconnectedness becomes even more acute when we look at the cutting-edge experiments being conducted in the realm of quantum electrodynamics, cavities. Scientists have recently figured out how to trap individual atoms inside hyper-reflective microscopic mirrors, spaced just wavelengths apart. By placing an atom inside this restricted geometry, they are doing something deeply radical. They are physically modifying the vacuum environment that the atom is allowed to interact with. Just like the Casimir effect boxes out certain wavelengths of virtual photons between two plates, A quantum cavity restricts the types of zero-point fluctuations that can exist around the trapped atom. Because the vacuum inside the cavity is suppressed, the atom's electrons find themselves unable to undergo spontaneous emission, the standard process where an excited electron drops down to a lower energy state by spitting out a photon. The atom's lifetime is artificially extended, its internal clock frozen, simply because the empty space around it has been systematically altered. Conversely, by tuning the cavity to resonate with specific virtual wavelengths, scientists can amplify the vacuum fluctuations, forcing the atom to interact with the zero-point energy at an accelerated rate. They can change the atom's chemical reactivity, alter its magnetic properties, and shift its spectral lines without ever touching the atom itself. They are controlling matter purely by editing the vacuum. These cavity experiments have triggered a quiet panic among engineers trying to scale up the first generation of commercially viable quantum computers. In a quantum computer, information is stored in the fragile superpositions of qubits. To perform a calculation, these qubits must remain perfectly isolated from the outside world. Any interaction with the environment causes a phenomenon called decoherence, where the quantum information leaks out, ruining the computation and introducing fatal errors into the system. Engineers have spent billions of dollars building ultra-advanced containment chambers, vacuum tubes that are emptied of every single stray molecule of gas, shielded by massive lead walls to block out cosmic radiation, and cooled by dilution refrigerators to temperatures colder than the deepest depths of interstellar space. They believed that by creating this ultimate pristine isolation, they could protect their qubits from the chaos of the world. But they forgot about the one thing you can never shield, the quantum vacuum itself. Even in a perfect, absolute zero laboratory void, surrounded by meters of lead and frozen to the brink of standstill, the zero-point fluctuations of the underlying quantum fields remain fully active. They cannot be turned off, and these irreducible background jitters are constantly whispering to the qubits. The random, unpredictable spikes of the vacuum fields collide with the delicate superpositions, triggering spontaneous phase flips and state transitions. The quantum computer's greatest enemy isn't external noise, or thermal heat, or faulty engineering. Its greatest enemy is the fundamental fabric of reality itself. The vacuum is an inescapable source of cosmic static that is constantly eroding our ability to control quantum information. To build a truly flawless quantum computer, we are being forced to develop complex error correction codes that are specifically designed to outsmart the nonstop subatomic sabotage of empty space. And this brings us back to the ultimate, profound discomfort that sits at the heart of this entire narrative. We have spent the last century building a civilization based on the mastery of matter. We learned how to manipulate silicon to build computers, how to split nuclei to generate power, and how to rearrange molecules to create modern medicine. We viewed the universe as a vast collection of material things, and we viewed ourselves as the masters of those things. But the deeper our quantum tools penetrate into the foundations of reality, the more that material empire begins to look like a castle built on sand. The solid, dependable world we touch and see is just a superficial ripple. Beneath it lies a volatile, non-local, hyper-entangled ocean of pure vacuum potentiality, a void that can manufacture matter out of tension, weigh down our bodies with its baseline energy, evaporate black holes, and rewrite the laws of physics at the speed of light. We are no longer just passive observers looking out at a cold, indifferent universe. We are active participants in a deeply interconnected, dynamic quantum system. Every time we turn on a quantum computer, every time we push an electric field to its limits inside a sheet of graphene, we are tugging on the invisible threads of the vacuum, testing the boundaries of the emergent illusion we call space-time. We used to look into the dark sky and feel small because of the vast emptiness that stretched between the stars. But today, the discomfort is far more intimate. We are uncomfortable because we know that the emptiness isn't out there in the dark. The emptiness is right here, inside our rooms, between our thoughts and within the very cells of our hands, churning, fluctuating, and waiting for the right conditions to turn nothing into everything all over again. For centuries, our fundamental understanding of reality rested on a seemingly intuitive premise. If you clear away all the matter, shield a region from every passing wave of radiation, and lower the temperature to absolute zero, you are left with a pristine, inactive void. This classical perspective viewed the vacuum as the ultimate blank canvas, an inert geometric backdrop where forces play out but nothing intrinsic happens. Yet, the deep architectures of modern physics have revealed that this intuitive picture is completely wrong. What we call empty space is not empty at all. It is a restless, dynamic medium fluctuating with unseen energy. The void possesses structure, exhibits measurable physical behavior, and serves as a boundless reservoir from which physical matter can emerge under the right conditions. This revolutionary understanding is rooted in the framework of quantum field theory, the cornerstone of the standard model of particle physics. In this worldview, the universe is not populated by discrete, isolated particles navigating through an empty arena. Instead, the universe is filled with overlapping, universal entities known as quantum fields. An electron is not a solid microscopic sphere. It is a localized, concentrated ripple within a vast electron field that permeates every square inch of the cosmos. In the same manner, photons are the ripples of the electromagnetic field, and quarks are the local disturbances of the quark field. These fields are omnipresent and completely inescapable. You cannot remove them from space because they are the very fabric of space itself. Seeking a region of space completely devoid of these fields is as paradoxical as trying to study water after stripping away its wetness. When physicists define a quantum vacuum, they are not describing a state where fields disappear, but rather a state where every single field has dropped to its absolute lowest possible energy configuration, known as the ground state. Crucially, the fundamental rules of quantum mechanics dictate that this lowest possible energy state cannot be zero. The mechanism responsible for this irreducible baseline activity is the Heisenberg uncertainty principle. This foundational law asserts that nature places a strict limit on how precisely we can simultaneously know specific pairs of physical attributes. For instance, the more perfectly you pin down the spatial position of a particle, the more inherently uncertain its momentum becomes. This is not a shortcoming of engineering or human instrumentation. It is an intrinsic fuzziness written into the mathematical structure of the universe. Applied to the fabric of a vacuum, this uncertainty relation manifests between the value of a quantum field and the rate at which that field changes over time. A field cannot simultaneously sit perfectly at zero while its rate of change also remains perfectly locked at zero. Because of this restriction, every field undergoes a permanent, irrepressible jitter. These random variations around a zero average are known as vacuum fluctuations, and the physical consequence of this constant activity is zero-point energy. It represents the absolute minimum energy budget of empty space, an irreducible floor that remains when every single piece of matter that can be extracted has been removed. These relentless energetic jitters give rise to the phenomenon of virtual particles. Unlike real particles, which propagate through space independently and can trigger a physical detector, virtual particles are fleeting, transient disturbances in the underlying fields. They essentially exploit a loophole provided by the uncertainty principle, borrowing a packet of energy from the vacuum for a vanishingly brief window of time before immediately paying it back. According to these quantum rules, a vacuum can momentarily accommodate an excess of energy, provided the loan is settled rapidly. The larger the quantity of energy borrowed, the faster the timeline for its return. Within these incredibly brief intervals, this borrowed energy materializes as a paired set of a particle and its corresponding antiparticle. They emerge together, coexist for a split second, and then collide to annihilate one another, restoring the borrowed energy back to the background field. While these spectral pairs cannot be intercepted or directly observed mid-existence, as the act of measurement would disrupt the loop, their collective influence on real matter leaves an unmistakable, quantifiable imprint. The most famous macroscopic validation of these hidden fluctuations is an anomaly known as the Casimir effect, theorized by Dutch physicist Hendrik Casimir in 1948. He proposed a strikingly simple thought experiment. If you take two uncharged, highly conductive metal plates and place them incredibly close to one another inside a flawless vacuum, an attractive force will spontaneously pull them together. This attraction cannot be attributed to gravitational pull or conventional electrostatic forces. Instead, the cause lies entirely in how the physical plates alter the quantum geometry of the vacuum itself. In the wide open space outside the boundaries of the two plates, virtual photons of every conceivable wavelength are free to materialize and vanish without restriction. However, the narrow gap between the parallel plates acts as a selective filter. Only specific virtual photons, those whose wavelengths fit perfectly into the gap as exact multiples of their half-wavelengths, can materialize in that restricted zone. Any virtual photons with longer wavelengths are physically locked out. This creates a stark, measurable asymmetry in the quantum pressure of empty space. The sheer density of virtual photon activity on the outside of the plates exceeds the restricted activity within the gap, generating a net pressure that pushes the metal boundaries toward each other. Because the strength of this force escalates dramatically at microscopic scales, verifying it required extraordinary experimental refinement. It was not until 1996 that physicist Stephen Lamoureux successfully isolated and measured this phenomenon, demonstrating that the attractive force between surfaces in a vacuum aligned with Casimir's mathematical predictions to within a 5% margin. Modern repetitions of this experiment have achieved even greater precision across diverse geometries and materials, cementing the reality that zero-point energy exerts genuine physical pressure. Today, this deeply theoretical phenomenon has crossed over into the realm of practical microscale engineering. As engineers manufacture microelectromechanical systems and nanoelectromechanical systems, devices containing switches, gears, and actuators measured in micrometers and nanometers, they find themselves running directly into the Casimir force. If left unaccounted for, the quantum pressure of empty space can cause the ultra-miniaturized components of a silicon chip to spontaneously bind together, rendering the device useless. Conversely, contemporary researchers are looking for ways to harness this quantum quirk constructively. By carefully engineering the geometry and material composition of these tiny surfaces, physicists have successfully flipped the sign of the force, transforming the natural quantum attraction into a repulsive push. This opens up the radical possibility of using the vacuum itself to achieve frictionless quantum levitation for nanotech components, allowing mechanisms to hover and operate without ever making physical contact. While the Casimir effect reveals how the vacuum's energy can manipulate real objects, a far more profound phenomenon demonstrates that the vacuum can actually be forced to yield permanent, tangible matter, the Schwinger effect. The theoretical foundations for this idea date back to 1936, when Werner Heisenberg and Hans Euler analyzed how a vacuum would respond to an intensely concentrated electromagnetic background. Their math indicated that if an electric field becomes powerful enough, the quantum vacuum will destabilize entirely, causing real electron-positron pairs to spontaneously rip out of the void. The external electric field effectively warps the energy landscape of the vacuum, supplying the necessary work to transform transient virtual fluctuations into permanent, self-sustaining, real matter. In 1951, Julian Schwinger mathematically formalized this mechanism, deriving a precise threshold known as the Schwinger critical field strength. To trigger this spontaneous of matter at a significant rate, an electric field must reach 1.33 10 to the 18th power volts per meter. To comprehend the sheer scale of 1 quintillion 300 quadrillion volts per meter, consider that the internal electric fields operating inside state-of-the-art semiconductor microchips are measured in millions of volts per meter. While nature can achieve these extreme thresholds in highly localized environments, such as directly adjacent to a heavy atomic nucleus, generating and maintaining a uniform Schwinger-level field across a measurable volume in a laboratory requires a staggering concentration of energy. For more than 7 decades, this monumental engineering barrier left Schwinger's prediction completely unverified. The world's most sophisticated laser complexes, including the National Ignition Facility in the United States and the Extreme Light Infrastructure in Europe, have pushed the boundaries of light concentration to the absolute limit. Yet they are still working to fully realize the raw intensities needed to tear open the vacuum of empty space. A breakthrough, however, arrived from an entirely unexpected direction: the world of condensed matter physics and the discovery of graphene. Isolated in 2004 by physicists Andrei Geim and Konstantin Novoselov, a feat that earned them the 2010 Nobel Prize, graphene consists of a single layer of carbon atoms arranged in a flawless two-dimensional hexagonal lattice. The true magic of graphene lies in its internal electronic landscape. Electrons moving through this atomic sheet do not behave like typical charge carriers in an ordinary metal wire. Because of the unique way the material's carbon atoms share their electrons, the valence band and conduction band meet at precise coordinates in momentum space called Dirac points. Near these junctions, the energy of the electrons scales linearly with their momentum, diverging completely from the quadratic relationship seen in conventional materials. This linear dispersion relation is highly significant because it mirrors the exact behavior of massless relativistic particles moving through a vacuum. Instead of obeying the standard Schrödinger equation of classical quantum mechanics, the charge carriers inside graphene obey an effective version of the Dirac equation, which Paul Dirac formulated in 1928 to reconcile quantum mechanics with special relativity. Consequently, the electrons inside this two-dimensional carbon crystal act as if they possess no rest mass whatsoever, traveling through the sheet at a constant effective speed equal to roughly 1/300th the speed of light. This transformation turns graphene into an analog laboratory for testing high-energy quantum electrodynamics effects that would otherwise require cosmic or astronomical conditions. Because these effective particles are completely devoid of rest mass, the energy barrier required to separate them from their corresponding antiparticles, the vacant states in the valence band known as holes, is dramatically lowered. The critical field strength needed to trigger a Schwinger-style breakdown scales directly with the square of the effective velocity of the particles. Because the internal speed of light within the graphene system is 300 times slower than the true speed of light in free space, the threshold for pair production drops by a factor of roughly 90,000. This massive reduction brought the long-sought Schwinger critical field within the reach of ordinary laboratory equipment. By applying highly controlled, intense electric currents to precision-engineered graphene architectures, researchers finally observed the historic signature of the Schwinger mechanism. As the applied voltage climbed, the material exhibited nonlinear current voltage behaviors that perfectly matched the mathematical predictions derived by Schwinger, adjusted for the unique physics of the graphene crystal. The data held true across varying temperatures and field variations, marking the first time humanity successfully witnessed an electric field tear real current-carrying matter directly out of a system's vacuum state. The successful validation of the Schwinger effect reshapes our perspective on cosmic evolution and the earliest moments of our universe. One of the greatest mysteries in modern cosmology is baryogenesis, the question of why the observable universe is filled almost entirely with matter rather than an equal mixture of matter and antimatter. Standard cosmological models indicate that during the ultra-hot, ultra-dense aftermath of the Big Bang roughly 13.8 billion years ago, matter and antimatter were being generated and destroyed in a state of perfect thermal equilibrium. As the cosmos expanded and cooled, this fierce cycle subsided, leading to a near-total annihilation event. However, a minute primordial asymmetry existed. For every 1 billion antiparticles created, there were 1 billion and 1 regular particles. The entirety of the modern cosmos, from the grandest galaxies to the atoms in our own bodies, is composed exclusively of that surviving 1 part in a billion remnant. Explaining how this crucial asymmetry arose requires satisfying the criteria outlined by physicist Andrei Sakharov in 1967, which include a distinct departure from thermal equilibrium. The intense, highly energetic fields present in the immediate infancy of the universe could have triggered profound, non-equilibrium Schwinger-type pair production events. By analyzing how strong fields force particles out of the vacuum, physicists gain vital clues into the hidden mechanisms that broke the cosmic balance, ultimately allowing our material universe to exist. This dynamic nature of the void is also central to the strong nuclear force. the interaction responsible for holding atomic nuclei together and binding quarks inside protons and neutrons. Governed by the laws of quantum chromodynamics, the strong force operates via mediating particles called gluons, which possess a property known as color charge. A defining characteristic of this force is confinement. Quarks are fundamentally incapable of existing in isolation. They are perpetually locked within color-neutral composites, such as the trios that form baryons or the pairs that make up mesons. The reason for this strict isolation is that the strong force does not fade as quarks move further apart, which contrasts sharply with the behavior of gravity or electromagnetism. When you attempt to pull two quarks away from each other, the gluon fields between them condense into a highly concentrated, tense tube of energy called a flux tube. As the physical distance grows, the total amount of energy stored within this flux tube escalates linearly. Eventually, the tension becomes unsustainable. Rather than allowing a solitary quark to break free, the massive energy concentrated within the flux tube reaches a threshold where it triggers an automatic strong force version of the Schwinger effect. The vacuum destabilizes, undergoing a process known as string breaking. The field snaps, instantly using the accumulated energy to create a brand new quark-antiquark pair out of the void. These new particles immediately bind with the separating quarks, resulting in two distinct color-neutral hadrons. This continuous self-defense mechanism of the vacuum ensures that a completely isolated quark can never be observed in nature. Remarkably, this active participation of the quantum chromodynamics vacuum is what gives ordinary matter the vast majority of its weight. The quantum chromodynamics void is filled with a dense, persistent web of activity known as the quark condensate, where quark-antiquark pairs continuously form and interact. When you look at a proton, the intrinsic masses of its three constituent valence quarks account for a mere fraction of the proton's total measured mass. The remaining 99% of its mass is generated by the raw kinetic and binding energy of the swirling gluons and the structural energy of the surrounding quark condensate. This yields a profoundly counterintuitive realization. The physical weight of everything you encounter, from the ground beneath your feet to the mass of your own muscles, is not derived from solid atomic building blocks. It is the direct macroscopic manifestation of the vacuum energy bound within the strong nuclear force. On an even larger scale, the entire universe is shaped by the vacuum of the electroweak force, which is governed by the Higgs field. This universal field maintains a non-zero vacuum expectation value, meaning that even in its absolute lowest energy state, its average value across the cosmos sits at a substantial baseline of roughly 246 billion electron volts. As elementary particles navigate through the cosmos, their continuous interaction with this pervasive Higgs vacuum acts as a form of quantum drag, granting them their characteristic rest masses. A particle like the electron experiences a pronounced coupling to this background, making it relatively heavy, whereas a neutrino interacts with it barely at all, leaving it almost entirely massless. However, precision measurements of the masses of both the Higgs boson and the top quark have forced physicists to confront an uncomfortable possibility. Our current electroweak vacuum might not be perfectly stable. Instead, it may sit in a state of precarious metastability, acting as a false vacuum. This implies that while our universe has remained stable for billions of years, it might occupy a local energy valley rather than the absolute lowest possible energy state, the true vacuum. According to the laws of quantum mechanics, a system trapped in a false vacuum can theoretically escape via quantum tunneling if it receives a sufficient perturbation. If a localized patch of space were to undergo this vacuum decay, it would trigger a catastrophic cosmic chain reaction. A bubble of true vacuum would materialize and immediately begin expanding outward in all directions at the absolute speed of light. Inside the boundary of this expanding bubble, the laws of physics would be completely rewritten. The fundamental masses of particles would shift drastically, breaking the delicate chemical balances that hold atoms together. No stars, planets, or living structures could survive its passage. Because the bubble wall propagates at the speed of light, there would be no advanced warning. The cosmic reset would simply arrive instantly. Fortunately, rigorous mathematical calculations indicate that the probability of our vacuum decaying within any realistic time frame is infinitesimally small. The energy barrier protecting our current state is immense, suggesting a vacuum lifetime that stretches out to at least 10 to the 500th power years, a duration that dwarfs the current age of the universe. Furthermore, our cosmos provides its own empirical proof of stability. For billions of years, ultra-high energy cosmic rays have been streaking across the universe, colliding with interstellar matter at energies that far exceed anything humans can produce in particle accelerators like the Large Hadron Collider. The fact that these violent, high-energy impacts have never triggered a vacuum collapse offers strong real-world evidence that our cosmic void is profoundly resilient. The crisis emerges when physicists attempt to calculate what the vacuum energy density should be using the established principles of quantum field theory. When you sum up the zero-point energy contributions from the fluctuations of every known field in the Standard Model, the theoretical prediction yields a value that is larger than the observed cosmic acceleration by a factor of 60 to 120 orders of magnitude. A mismatch of 120 orders of magnitude is a number represented by a 1 followed by nearly 120 zeros. This catastrophic disagreement highlights a profound breakdown in our current understanding of how quantum mechanics hooks into the gravitational geometry of spacetime. To bridge this gulf, theorists have proposed extensions to the Standard Model, most notably supersymmetry. This framework suggests that every known particle possesses a yet undiscovered heavy partner particle. Because bosons and fermions contribute to the vacuum energy with opposite mathematical signs, their fluctuations would naturally cancel one another out. However, extensive runs at the Large Hadron Collider have failed to turn up evidence of these supersymmetric partners at the expected energy scales. Even if supersymmetry exists in a broken form, it would only narrow the theoretical discrepancy down by about 60 orders of magnitude, leaving a massive, unexplained chasm. Resolving the cosmological constant problem remains one of the ultimate goals of modern physics, a solution that will likely require a complete, unified theory of quantum gravity. The profound interplay between the quantum vacuum and intense gravitational fields is demonstrated at the edge of black holes through a phenomenon known as Hawking radiation. In the classical framework of general relativity, a black hole is an absolute one-way cosmic drain. Once any object or ray of light crosses the invisible threshold of the event horizon, the escape velocity exceeds the speed of light, rendering escape impossible. However, in 1974, Stephen Hawking introduced quantum mechanics into this stark gravitational picture, focusing specifically on how an event horizon affects the ever-present vacuum fluctuations occurring right at its border. When virtual particle-antiparticle pairs spontaneously materialize from the vacuum directly on the perimeter of an event horizon, the extreme gravitational tidal forces of the warped spacetime can violently rip the pair apart before they can collide and annihilate. One member of the pair is pulled backward across the event horizon, trapped forever inside the black hole. Meanwhile, the orphaned partner particle is flung outward into the open universe. To an outside observer watching from a safe distance, this escaping particle appears as a steady stream of thermal radiation emanating directly from the black hole. Because the universe must strictly conserve energy, the newborn particle cannot simply materialize for free. The energy required to sever the virtual pair and launch the escaping particle is paid for by the black hole's own gravitational field. As a result, the black hole loses a fraction of its mass. Over incomprehensibly vast stretches of time, this continuous leak causes the black hole to slowly shrink, accelerating its mass loss until it eventually vanishes entirely in a final energetic burst. The temperature of this Hawking radiation is inversely proportional to the total mass of the black hole. For an ordinary stellar mass black hole created by the collapse of a massive star, its quantum temperature sits at a fraction of a degree above absolute zero. Because this is far colder than the ambient temperature of the cosmic microwave background radiation left over from the Big Bang, these macroscopic black holes are currently absorbing far more environmental energy than they radiate, meaning they are growing rather than shrinking. Only when the universe expands and cools far below their internal Hawking temperature will these giants begin their incredibly slow, multi-billion year process of evaporation. Conversely, if a miniature black hole with the approximate mass of a small mountain, roughly 10 to the 12th power kilograms, existed today, its Hawking temperature would match the current temperature of the cosmic microwave background, placing it in a delicate thermal equilibrium with the modern cosmos. While we have no observational evidence of these primordial microblack holes, their final explosive stages would leave a distinct signature of high-energy gamma rays. Because the Hawking radiation emitted by actual astronomical black holes is far too faint to be detected by modern telescopes against the noisy backdrop of space, physicists have turned to building high-fidelity analog systems in laboratories. By engineering environments where the physics of an event horizon can be accurately mimicked using flowing mediums, scientists can study how quantum vacuums behave near absolute boundaries. A landmark success was achieved in 2019 using an ultra-cold Bose-Einstein condensate composed of rubidium atoms. By manipulating the flow velocity of the condensate, researchers created an acoustic horizon, a point where the flow of the fluid exceeds the local speed of sound, preventing sound waves, or phonons, from escaping. Upon analyzing the acoustic vacuum fluctuations at this artificial horizon, scientists discovered that the escaping phonons displayed a distinct thermal spectrum that perfectly matched the temperature profile predicted by Hawking's equations. While these fluid experiments do not replicate the true gravitational mechanics of a spacetime anomaly, they definitively validate the core quantum field behaviors that drive Hawking radiation, proving that boundaries can manipulate the vacuum to generate real, detectable outputs. Ultimately, these diverse phenomena, from the microscopic pull of the Casimir effect and the materialization of matter via the Schwinger effect, to the structural weight of the quark condensate, the existential threat of vacuum decay, the mathematical crisis of the cosmological constant, and the slow evaporation of black holes, point to an identical conclusion. The quantum vacuum is not a passive, empty stage. It is a highly active, complex physical system that underpins the entirety of our material reality. The long-standing intuition that a void is inherently inert has been thoroughly dismantled by decades of precise laboratory validation. Space is not merely a container for matter. The fluctuations of its fields are what give space its fundamental substance, continuously demonstrating that everything we see, touch, and are is intimately connected to the restless energy of what appears to be absolutely nothing. Fexel's quantum vacuum explorations explains how advanced laboratory simulations are forcing physicists to confront the unsettling complexities of false vacuum decay and the deep structural mysteries hidden within the quantum void. The deeper physicists probe into this energetic backdrop, the more uncomfortable the implications become for our traditional views of causality, permanence, and the fundamental laws of nature. If the vacuum is a dynamic ocean of potential, then every piece of matter in the cosmos is merely a transient wave crest on its surface. This realization forces a complete inversion of how we conceptualize the universe. Instead of matter being the primary ingredient that inhabits an empty stage, the vacuum itself is the primary medium, and matter is merely a secondary structural byproduct of its internal physics. This conceptual shift has opened up entirely new domains of inquiry, challenging the boundaries where quantum mechanics, general relativity, and thermodynamics collide. To understand why this makes scientists so deeply uncomfortable, one must look at how these vacuum fluctuations fundamentally complicate the concept of information conservation. In classical physics, if you know the exact positions, velocities, and properties of every particle in a closed system at a given moment, you can theoretically use the laws of physics to reconstruct the entire past history of that system and predict its entire future with absolute certainty. This is the principle of determinism. Quantum mechanics complicates this with its inherent probabilities, but it still maintains a strict law known as unitarity. The total sum of all probabilities in a quantum system must always equal exactly 1, and the past state of a quantum wave function uniquely determines its future evolution. Information, in the quantum sense, can never be truly destroyed or created from absolute nothingness. Yet, the persistent activity of the quantum vacuum appears to constantly push against the edges of this rule. Consider the localized behavior of virtual particles interacting with real, stable matter. When a virtual electron-positron pair materializes adjacent to a real electron, the real electron does not simply ignore them. Because like charges repel and opposite charges attract, the real electron physically repels the virtual electron and attracts the virtual positron. This behavior, known as vacuum polarization, effectively clouds the real electron in a protective shroud of virtual antimatter. When an experimentalist attempts the charge or mass of an electron from a distance, they are not measuring the bare properties of the isolated electron itself. They are measuring the net effect of the electron plus its surrounding cloud of vacuum polarization. As you probe closer to the electron using higher energy particle colliders, you pierce deeper through this screening cloud, and the measured effective charge of the electron actually increases. This means that the fundamental constants of nature, the numbers we write down in textbooks as the unchanging properties of the universe, are not static values at all. They are running coupling constants whose values are explicitly dictated by how heavily the quantum vacuum screens them at different energy scales. This constantly shifting background implies that every single calculation in quantum field theory is plagued by infinities. If you try to calculate the total energy of the vacuum by summing up the zero-point energies of every single possible wavelength of every quantum field down to infinitely small distances, the mathematical result is not a large number. It is literally infinity. For decades, physicists were forced to employ a highly controversial mathematical trick known as renormalization to bypass this roadblock. By subtracting one infinity from another in a carefully controlled manner, theorists could isolate the finite differences that correspond to real, measurable physical effects. While renormalization yields predictions that match experimental data to unprecedented precision, such as the anomalous magnetic dipole moment of the electron, which matches theory to more than 10 decimal places, many founding fathers of quantum mechanics were deeply unsettled by it. Paul Dirac himself openly expressed disgust with the practice, referring to it as a mathematically unsound trick rather than a true description of nature. The necessity of renormalization strongly suggests that our current models are merely effective field theories, low-energy approximations of a deeper, more fundamental layer of physics that we have yet to uncover. This brings us back to the uncomfortable reality of the cosmological constant problem, which takes these mathematical infinities and scales them up to the size of the entire universe. If the infinite energy of the quantum vacuum is real enough to polarize electrons and push metallic plates together via the Casimir effect, then, according to Einstein's general relativity, it must possess gravitational weight. In the framework of general relativity, gravity does not care about the origin of an energy source. Any form of energy density possesses mass equivalence and must bend the geometry of space-time. If the vacuum energy density truly matched even the most conservative quantum field calculations, the gravitational consequence would be immediate and catastrophic. The enormous energy density would cause space-time to warp so violently that the universe would have undergone an explosive, hyper-accelerated expansion within a fraction of a second after the Big Bang, tearing apart every atom before stars or galaxies could even begin to coalesce. The very fact that you can read these words, that galaxies exist, and that the universe expands at a comparatively gentle, measurable pace is absolute proof that the calculated vacuum energy is somehow prevented from exerting its full gravitational weight on the cosmos. This glaring contradiction is what makes the cosmological constant problem the ultimate crisis in modern physics. It reveals an unresolved rift between our description of the microscopic world, quantum field theory, and our description of the macroscopic world, general relativity. One of the two frameworks is fundamentally missing a crucial mechanism. Some theorists speculate that there must be an undiscovered symmetry or a dynamic cancellation mechanism that perfectly suppresses the vacuum energy's gravitational footprint. For example, in an ideal implementation of supersymmetry, Every single boson fluctuation would be accompanied by a fermion fluctuation of the exact opposite sign, resulting in a clean mathematical cancellation that drops the total zero-point energy down to zero. However, because our universe is visibly not supersymmetric at the energies we can observe, electrons do not have selectron partners with the same mass. Supersymmetry must be broken. Once the symmetry is broken, the perfect cancellation falls apart, and the predicted vacuum energy shoots back up by dozens of orders of magnitude, failing to solve the mystery. Other researchers look toward the exotic landscape of the string theory multiverse for an answer, an approach that makes many traditional physicists even more uncomfortable. According to certain formulations of string theory, there are up to 10 to the 500th power distinct, mathematically permissible configurations for the extra dimensions of space-time, each yielding a unique vacuum state with its own specific cosmological constant. In this anthropic interpretation, the vast majority of these pocket universes possess vacuum energies so massive that they either collapse immediately or fly apart too fast for life to form. We find ourselves living in a universe with an absurdly fine-tuned, near-zero cosmological constant simply because it is one of the exceptionally rare configurations where the vacuum is gentle enough to allow stars, planets, and intelligent observers to evolve. To many scientists, relying on the anthropic principle feels like an admission of defeat, a retreat from seeking a rigorous, first principles physical law in favor of a cosmic lottery explanation. While cosmologists grapple with the macro-scale vacuum, condensed matter physicists are actively using analog materials to study how the vacuum can be manipulated to create entirely new phases of matter. The success of confirming the Schwinger effect in graphene has sparked a revolution in laboratory astrophysics. By constructing complex heterostructures, stacking layers of graphene, boron nitride, and other two-dimensional materials at precise relative twist angles, researchers can create synthetic quantum vacuums with tailored properties. In these Moiré superlattices, the effective speed of light and the interactions between particles can be dialed in by changing the physical orientation of the sheets. This allows scientists to simulate how quantum fields behave under extreme conditions that are completely inaccessible in conventional laboratories, such as the ultra-intense magnetic fields surrounding magnetars or the highly distorted spacetime geometries near the horizons of cosmic strings. These material analogs have also shed light on the elusive nature of topological vacua. In advanced quantum materials, the ground state, the local vacuum, can possess a non-trivial global shape or topology. Just as a donut is topologically distinct from a sphere because it contains a hole that cannot be removed by continuous deformation, a topological vacuum possesses global properties that are completely protected against local defects or thermal noise. When excitations emerge from these topological vacua, they do not behave like ordinary electrons or holes. Instead, they can manifest as fractionalized quasiparticles that carry a precise fraction of an electron's charge or exhibit entirely different quantum statistics known as anyons. The discovery that manipulating the boundary conditions of a local material vacuum can force the emergence of entirely new classes of stable fractionally charged particles reinforces the fundamental lesson of modern physics. The vacuum is not a blank void, but a highly customizable generative matrix. This generative power of the vacuum becomes explicitly clear when examining the physics of the early universe during the epoch of cosmic inflation. According to inflationary cosmology, the universe underwent a period of exponential expansion within the first trillionth of a trillionth of a trillionth of a second after the Big Bang. During this hyperexpansion phase, the fabric of space was stretching at a rate far faster than the speed of light. This rapid expansion had a profound effect on the primordial quantum vacuum fluctuations that were occurring at the time. Before a virtual particle pair could annihilate and return its borrowed energy to the background field, the rapid stretching of space caught them, physically ripping the two particles apart and dragging them across macroscopic distances. The transient subatomic jitters of the vacuum were suddenly frozen in place, amplified by the expansion into permanent macroscopic variations in the density of energy across the cosmos. These frozen vacuum fluctuations became the primordial seeds of all cosmic structure. As the inflation era ended, the regions of space that happened to have slightly higher energy densities due to a random quantum fluctuation exerted a slightly stronger gravitational pull on surrounding matter. Over billions of years, these dense patches pulled in more gas, eventually collapsing to form the very first stars, protogalaxies, and cosmic filaments. When astronomers look at the cosmic microwave background, the ancient afterglow of the Big Bang mapped out by satellites, they observe a delicate pattern of hot and cold spots across the sky. These temperature variations match the statistical distribution of quantum vacuum fluctuations predicted by inflationary theory. This yields one of the most astonishing realizations in science. The grandest structures in our universe, the massive superclusters of galaxies spanning billions of light years, are nothing more than the magnified frozen whispers of subatomic vacuum fluctuations that occurred at the dawn of time. If the vacuum could be stretched to create galaxies in the past, could it be manipulated to propel humanity across the stars in the future? This question lies at the heart of advanced propulsion concepts that push the absolute limits of known physics. In 1994, theoretical physicist Miguel Alcubierre demonstrated that within the framework of general relativity, it is mathematically possible to construct a warp drive. The Alcubierre metric describes a configuration where space-time is artificially compressed in front of a spacecraft and expanded behind it. The ship itself sits inside a localized bubble of flat space, riding the warping of space-time like a surfer on a wave. Because it is space-time itself that is moving and expanding rather than the ship traveling through space, the bubble can theoretically propagate at any arbitrary speed, bypassing the universal speed limit imposed by special relativity without violating local physics. However, the catch is monumental. To generate the specific space-time geometry required for a warp bubble, the equations demand a vast amount of exotic matter possessing negative energy density. In classical physics, negative energy density is an absolute impossibility. Energy is strictly positive. But as we have seen, the quantum vacuum via the Casimir effect regularly demonstrates localized regions of negative energy pressure. By placing reflective surfaces or utilizing extreme electromagnetic fields to suppress certain wavelengths of vacuum fluctuations, physicists can technically create local zones where the energy density drops explicitly below the baseline ground state of the surrounding space. While the total energy of the broader system remains positive, these localized quantum negative energy states are real and measurable. Whether these quantum effects can ever be scaled up or stabilized to manipulate spacetime on a macroscopic engineering scale remains highly speculative. But the mere fact that the quantum vacuum offers a theoretical loophole for generating negative energy continues to captivate advanced propulsion researchers. The dynamic nature of the vacuum also forces a reassessment of the ultimate fate of the universe. If our universe occupies a metastable false vacuum, the timeline for its survival is not dictated solely by the gradual cooling of stars or the slow evaporation of black holes via Hawking radiation. Instead, it is vulnerable to a random event of vacuum decay. The concept of a false vacuum can be visualized as a ball resting in a shallow depression high up on the side of a steep mountain. The ball is stable against small disturbances, but if it tunnels through the small ridge holding it in place, it will rapidly roll down to the true valley floor below. The probability of this tunneling event occurring increases dramatically in the presence of extreme energy concentrations. This realization initially sparked public anxiety during the startup phases of massive particle accelerators like the relativistic heavy ion collider and the Large Hadron Collider. Critics worried that slamming subatomic particles together at near-light speeds might concentrate enough energy in a microscopic volume to act as a seed, overcoming the local energy barrier and triggering a localized vacuum collapse that would swallow the Earth. Physicists were able to confidently dismiss these fears by pointing out that nature routinely performs far more violent experiments across the cosmos. Cosmic rays with kinetic energies millions of times greater than anything achievable in human colliders have been slamming into the atmospheres of planets, the surfaces of dense neutron stars, and the interstellar medium for billions of years without ever initiating a vacuum collapse. The continued existence of ancient astronomical bodies provides an empirical ceiling on the likelihood of accidental vacuum decay. Nevertheless, the theoretical vulnerability remains. As the universe continues to expand and mature over trillions of years, the probability of a spontaneous quantum tunneling event occurring somewhere in the vast expanse of space slowly accumulates over an astronomical time frame, stretching out to timescales like 10 to the 500th power years. Vacuum decay ceases to be an impossibility and becomes a mathematical certainty. The universe as we know it will eventually be overwritten by a new set of physical laws, born from a single quantum transition within the void. This close tie between the vacuum and the laws of physics introduces a radical concept known as vacuum engineering. If the properties of elementary particles are explicitly dictated by their interactions with the surrounding vacuum fields, such as the electron gaining its mass from the Higgs vacuum or its charge being screened by vacuum polarization, then if you can successfully manipulate the structure of the local vacuum, you can theoretically alter the properties of the matter residing within it. This is not just science fiction. It is already beginning to happen on a microscopic scale within the field of cavity quantum electrodynamics. By trapping atoms inside highly reflective optical cavities whose physical dimensions are perfectly matched to specific atomic transitions, physicists can suppress the zero-point fluctuations at certain frequencies. Without the necessary vacuum fluctuations available to stimulate spontaneous emission, an excited atom trapped inside the cavity can be explicitly prevented from dropping to its lower energy state. Its lifetime is extended indefinitely simply because the surrounding vacuum has been stripped of the specific fluctuations needed to allow the transition. Scaling this capability up to alter macroscopic material properties is one of the most exciting frontiers in modern condensed matter physics. Researchers are experimenting with placing complex materials inside optical cavities to see if the modified vacuum fluctuations can induce high-temperature superconductivity, alter chemical reaction rates, or induce novel magnetic phases without applying external heat or pressure. By tailoring the electromagnetic vacuum environment enclosing a substance, you can force its electrons to self-organize into entirely different configurations. The implications for manufacturing, quantum computing, and materials science are staggering. We are moving away from an era where we simply manipulate the atoms themselves and entering an era where we manipulate the empty space around the atoms to redefine how they behave. This brings us to the core irony that makes modern scientists so profoundly uncomfortable. Our deepest description of the material world relies entirely on the properties of a medium that we cannot directly see, touch, or easily isolate. The solid, stable reality we experience every day is an illusion generated by a restless, unseen ocean of quantum activity. Every breath we take, every star that shines, and every galaxy that drifts through the cosmic deep is explicitly shaped, sustained, and weighted by the zero-point energy of fields that permeate the void. The successful confirmation of the Schwinger effect in graphene has proved beyond any doubt that this hidden landscape is fully real, capable of responding to human intervention and yielding permanent physical matter from what appears to be absolute nothingness. As we continue to refine our ability to engineer the vacuum, probe the limits of black hole horizons, and decipher the cosmological constant problem, we are constantly reminded that empty space is not a passive canvas. It is a living, dynamic matrix, the foundational bedrock of the universe, holding the keys to where our cosmos came from, how it operates today, and how it will ultimately end.